All right. So I'm going to share my screen because I think this will be working better if you can see what I'm doing. Um, and let me know if there's any issues. Okay, so what I'm going to do today is walk you through how to run GSAS-II, and hopefully I'll be able to do a couple of examples for you and do them successfully. It's always a question, right? So sometimes you get them right, sometimes it just takes you a little bit longer. These should be fairly straightforward. So I have one example from 11BM, which is the powder diffraction line at the advanced photon source, and we'll start with that. So the program is called GSAS-II, and that's General Structure Analysis System, and it can do single crystal, powder diffraction. It can do some amount of structure solution, so unknown structures. It can do some work on PDF, a pair distribution function measurements as well. So it's really a one and all type of program. It's all written in Python, and it's continually maintained by Brian Toby and Bob Von Driel. Down here, you can see the primary citation. The original program GSAS-I or GSAS was all written in Fortran, and it was closed source. This is basically open source because it's all Python. And so you can take a look and make changes and make suggestions, and they have a Git page where you can submit changes if you like. But you can download it from this site. You notice it's not Git. I'm sorry, Subversion at Argonne National Laboratory. And so Brian is at Argonne National Laboratory. Bob was at Argonne National Laboratory before he retired. And you can install it on Windows, Mac OS X, Linux, or you can do an Anaconda installation where you install a whole Python environment on your particular program, and it's all sort of an isolated Python environment. So I'm running it on a Linux system, and I've installed it by hand because that's just sort of what I prefer to do. So I don't like to put desktop desktop icons for launching programs. I prefer to find them in my my toolbar, or I just run them from the command line. That's just more convenient for me. So what do we have to work with today? So I've set up a directory, and I have some data for magnesium chromate, MgCr204. And that's from 11BM. So let's go into that directory and see what we got. I don't know if I put anything in there yet. No, nothing yet. So I have to go up a couple directories, and I'll show you what we get from 11BM. So the data when you send a sample in your mail-in program, you get back a zip file that contains two files. One is this FXYE file, and the other one is a PRM file. So this contains the actual data, and this contains the parameter file for 11BM. So this is an important file because you need this to get the instrument parameters. So let's take a look at these, and we can just look at them with a text editor and see what they look like. So this is FXYE has angle. In this particular case, this is angle, counts, and error. That's the Y. The E at the end is for error or estimated standard deviation. Basically, it's a Poisson error. And then it has additional information up here. This was taken by Saul Lapidus, and he generously gave me the data so I could use something nice to demonstrate on. And so this is it's a pellet of MgCr204 on Kapton. And that's what we're going to work on. There's 34,000 data points on this. And this is all done through the automatic system. So goniometer radius, all that stuff is in this, is also in the parameter file. So if I look at the PRM file, it has that information in a compact form so that you can load it up into GSAS. It has some information about how the profile instrument profile was calculated. It's generally done with lanthanum hexaboride, which is what we do also in our diffractometer. That's a resolution standard. So, okay, so where do we start? Well, the first thing we want to do is we know that this is magnesium chromate, and it's a spinel. So we've got to get information on this system. So I generally go to the ICSD website. That's the easiest place to go to. It's online. You can have a demo account. You don't have to have an actual account, but we do have a site license for the university of 4 accounts. And if you need to use it, you just ask me, I'll assign you one of the 4 passwords, and other people can use it too, as long as 2 people aren't using it simultaneously. So let me just go through a chemistry search. So this is where we're doing a chemistry search like this. And I'm going to do it for the magnesium chromate, MgCrO. So these are 3 elements. I'm going to say there's 3 and only 3 elements. And then I can make if I want, I can use this for the structural formula. This would be MgCrO2O4 with spaces in between. And then I run the query, and I will get whatever is in the ICSD database. In this particular case, there's less than 20 different data sets. You sort of have to think about it. You can see the space group here and the formula. So this is all going to be pretty much the same because I searched on that. Then the structure type, then the publication, from the title of the publication from which this comes, and the authors, and the journal with the date and reference. So you can go and find that reference information. Good patterns have stars on them. And so these are all very good patterns. The data is high quality. Turns out that all we really care about is this first one, which is a spinel, and it has a cubic structure, but very large cubic structure with lots of formula units per unit cell. And you can see the lattice parameters are 8.334 and 90 degrees. And this is a diamond, face-centered diamond type structure. It's certainly a face-centered structure. Okay, we don't need to worry about this. What we want to do is download it. And this is the one I've downloaded already before. So if I look up here over on the right side, you can see I've downloaded the magnesium chromium 204 75623, which is this top one. And that's the one we're going to work with. So let me close this for the moment. And now let me open GSAS-II. So when it opens, it gives you 2 windows, a main window and a plot window. So the main window has nothing in it when you first started. And you can open a new structure. You can open a previous data refinement, and lots of different things you can do. But we will open, and we have a new project. The first thing we're going to do is we're going to import data. So you import powder data, and we're going to import it from a GSAS powder data file. And that includes the FXYE type file. It also includes the GSAS type file. So I'm going to move up to the top directory, and there it is. There's the data set. So I'm going to open this up, and it asks me whether I'm going to read it. It tells me what's in there. And I'm going to say yes. And then this contains already some information about the instrument, I believe. Yes, it does. So the instrument file, it tells me the wavelength. It tells me the polarization is 99% horizontal. And it gives me some line width parameters, which are plotted here, which are very specific to 11BM, which are calculated from the lanthanum hexaboride. Now, this is the FXYE file, has that data already in there. If I had a GSAS file, then it would ask me for a parameter file, and I would load that separately. But GSAS-II understands that the FXYE file has data in it already. And so over on the right side, you see a plot of the different components, the Gaussian, the Lorentzian, and the sum of Gaussian and Lorentzian. So basically the Lorentzian, there is no Lorentzian component to this line. It's a Gaussian from the advanced photon source. That's sort of typical of a synchrotron. And so the red line you don't even see because it's hidden underneath the blue line. Okay. If you were taking data from the powder diffractometer that we have here in the synchrotron center down in room 50, then you would notice that there's Gaussian and Lorentzian components to it because it is a laboratory instrument. The geometry is different. This, if you recall, is in the Laue geometry. So if we now go back to here, we will see a plot of the data. And you can see that the data is out to 50 degrees, but this is 50 degrees with a wavelength of 0.45, so it's a high energy. And the despacing, therefore, can be fairly small out here. And you can move around and you can look at what the data says. So if I go to the top of this peak, I see that 2 theta is 17.885, the despacing is 1.47, and the intensity is 72,000 roughly. So this is the data set we're going to work with. We now want to import a structure. So what we're doing here is refining the structure. We're not solving a structure. Solving a structure is much more involved. And you can find tutorials on the GSAS website which will show you how to do some of these things. So when I want to import a structure from a CIF file, a crystallographic information file, I will just go, I can import it from a previous old style GSAS refinement. I can import it from a new style GSAS refinement, or I can import it from a CIF file or any number of other things. Or I can guess the format from the file. But I want to get a CIF file, makes it easier. I know that's what I have. So this is my CIF file. I'm going to open this up. It says yes. And then it asks me what this is. This is chromium manganese oxide. I prefer to write it as MgCr2O4. And then it asks me which powder data I want to associate with this structure with. And there's only one, and I better associate it or else I can't refine anything. So I associate it with that file and I click OK. And now I have something in this panel. So the first part of the panel here is general information that is extracted from the CIF file, like the structure, the space group, unit cell parameters. Obviously, there's only one parameter because it's cubic. The angles are all 90 degrees. A box for whether I want to refine this, tells me the density and the composition. You see it's magnesium, chromium, and oxygen. And it has information about these three elements that are in there. Everything down here is used for structure solution. We don't need to do it for refinement. Pauli and then Fourier mapping and charge flipping and Monte Carlo simulated annealing, all these are used to solve an unknown structure, which is, as I said, quite involved. But there are tutorials there that you can learn from. The next tab has data. And this has information about some of the parameters that you can refine. You notice you have, I've used this histogram for this data set. Then I have a phase fraction. There's only one phase, so this is going to be 1. I'm not going to refine this. Then I have a size broadening term, domain size model, which if I refine it, I can use isotropic or uniaxial. Cubic materials generally are better isotropic because they're pretty isotropic. And if you want to refine this, you click this button and it refines. You have a strain broadening model, which is either isotropic or non-isotropic. And then you have these additional strains which can also be used as different subtle refinements. And unless you really know what you're doing, you don't use this. However, preferred orientation is possible, especially if you have samples that have platelet orientation or platelet dimensions. They might be lying down as you prepare your sample, you flatten it out, you might have preferred orientation. That is not generally the case with the 11BM data, because as I mentioned before, you have a small capillary, so you're going to not really pack it and tamp it down to orient, but then that is rotated. And so you'll have pretty much a good powder diffraction pattern with no preferred orientation with 11BM data. And preferred orientation, if you're going to use it, you can use this Marsh-Delays method, which is a single parameter, or spherical harmonics, which is the one I prefer to use when I do use this. You can have extinction. I frankly have never needed to use any of these parameters. But again, I am not a crystallographer, so some people certainly will use them. Otherwise, they wouldn't be there. You also have here a background. Now, the background here is pretty flat, but we still need to fit it with something. And typically, the best way to use the background function is to use the Chebyshev polynomials. And we're going to refine it. It's set up to refine. And right now it says 3 coefficients. I like to start at 6 for something that's sort of flat. That's usually good enough. Sometimes I have to go higher if there's a lot of structure to the background. We'll see how that works out and whether we need anything better. And these are all going to be refined. Again, I do not use these a lot, but you can add peaks to the background. For example, if you have an amorphous peak, you can add a peak here and just make it really broad and fit it as a peak that doesn't correspond to the structure, but corresponds to an amorphous material. And that's also possibly done. You can also, you can do point-by-point subtraction of an interpolated linear fit to the background. But the Chebyshev polynomials usually work pretty well. You then have instrument parameters. Well, let me go up here. Limits is the limit of the data. And even though it doesn't look like there's much out here, we can zoom in. Oops, we can zoom in and take a look. Oops, oh, what did I do? Oh, I used the wrong ones. Okay, sorry. You can see there are some very nice sharp peaks here, and they're very distinct. So very sharp, very nice. We're going to use all the data that we have, basically. So the limits are the angular limits. In this case, it goes from 0.5 to 50. And we're going to leave it like that. Sometimes you might want to cut off at the low angles if you have a background that slopes up very rapidly like you do in the laboratory diffraction system. But for this, don't worry about it. You don't worry about it. The instrument parameters, as we talked about before, there's lambda in a Bragg. This is a Lau geometry. In our diffractometer at the university, we have two wavelengths. We will have K alpha 1 and K alpha 2 for copper. That's typically the tube that we use. And so you will see 2 lambdas here with different ratios. But in this case, since you're at a synchrotron, you have a very monochromatized beam, you know what the energy is, and there's only one of them. 0 is for displacements of the diffractometer. And in fact, this is not perfect, but there's generally for 11BM, there's 2 displacements. There's an X and a Y displacement. And so in this case, since it pulled the data in from the FXYE it didn't ask us for a parameter file. So I could probably import a parameter file here. Let me see if I can import a new parameter file. Oh, maybe not. Let's see. I'm going to see if I can run it like this, but often it's better to use the actual parameter file. For some reason, it was smart enough and picked up whatever was in the header file of the file, data file, and didn't ask me for a parameter file. So I might be able to load a new parameter. Oh, load the profile. Okay, so let me load a profile. And usually it asks you this, but in this case it did not. Let's see. 570. Oh, wonderful. It is not showing me. Set from default. Let's see. No, I don't want that. If I can, I'll go back into the. You know what? Let me just go and 30K 11 DM. That's not what I want. Let me change the name of this file. See if I can do that. If it works. We'll see if it picks it up. There we go. Yeah, it's not doing anything different. It's the same. Okay. Not to worry. Apparently, this is good enough for this particular data set. In the newer ones, they have X and Y displacements for the sample. Oh, there it is. There it is. I'm sorry. Sample X displacement. There it is. It's sitting here. I knew it was there somewhere. Okay. So these sample parameters are the last thing, and the histogram scale factor tells you how big to make the peaks. So this is something that will be varied, and the goniometer radius is fixed. This is a sample X displacement and Y displacement, parallel and perpendicular to the beam, if it's not exactly centered in the goniometer. So sometimes one of these is usually the one you need to adjust. So this is if the beam is a little bit higher, a little bit low. This is if the beam is, if the sample is not exactly at the center of rotation of the goniometer along the beam direction. So we don't really need to worry about these too much until we do the refinements. So what do I refine first? Well, I always want to refine the background first. So that's the first step, is always the background. So the background's already being refined. I'm going to use a histogram scale. I'm going to allow the histogram scale factor to vary. But if the peaks are not in the right place, it might be a little bit tricky. So let's see what happens and decide whether we have to adjust it. So whenever you do a refinement, you always have to release parameters one at a time and be a little bit careful about it. So up here in the calculate menu, you can refine. Remember, we're refining now the background, 6 parameters, and the histogram scale factor, and nothing else. And let's see what it does. So I'm going to put this in this directory and call this 11 BMB 1733, and that's a .gpx file. And so it's going to refine, and you can see that it reports some value. So there's a 48.9898 weighted profile, which is very poor. You need to get much better than that. And you can see here, if I zoom in, oops, let me say okay first. You zoom in, that the peaks, it's hard to see, but the green is the fit. So you see the fit is here, it's a small peak, it's in the right place, but it certainly doesn't meet the intensity. Right, so the shape looks pretty good, the intensity is a little bit off. So clearly we're not quite in the right place. The histogram scale factor is just 1, which is fine. And so we have to start freeing up some additional parameters. So the background is, you can see now you should have 6 parameters. So what we're going to do is now refine again. We only did, if you look at how you're set up for refinement in the controls, you only do 3 cycles at the beginning, because you don't want it running off and going off in the refinement where it's not where you want it to be. If you run 20 cycles, it can easily get off. So let's just refine again and see if we do any better with our weighted profile. It doesn't. So we've reached the limit of what we can do with these 2 parameters. So we loaded up, and now we're going to start adding additional parameters. So the first thing we can do is to allow the unit cell to be refined. So that adjusts this value, and that means the peaks will all adjust a little bit. And if you look out here, right, the peaks are close, but they may not be close enough to be right in exactly the right spot. So let's see what we can get. So if I now have 3 parameters, well, I have 6, 7, 8 parameters now. I'm going to refine again and see if I improve my refinement. A little bit, not much. So the lattice parameter is pretty close to being correct, and that's fine. Okay. All right, that's as far as I'm going to get. So what else is there that I can adjust? And that's always the trick. The background looks like it fits nicely. 6 parameters is plenty. The lattice parameter is the simplest thing to lock in. Once it's there, it's there. I can now look at this tab, and I could change the size and see if there's a size broadening or a microstrain broadening. But that's usually not the first thing to try for samples that are so sharp. These peaks are very sharp. Instead, let's look at the structure. So notice that we have 3 atoms in here. We have magnesium, chromium, and oxygen. And this is an 8-fold position. This is a 16-fold position. This is a 32-fold position in the crystal structure. And you can see this is 1/8, 1/8, 1/8. That's a special position. And if you move off of this position, you can't really change X, Y, or Z. Same thing here, 1/2, 1/2, 1/2. That's a special position. Things like 1/4 and 1/2 and 1/3, those are always special positions. This, however, is not a special position, right? So this is 0.26, 0.26, 0.26. So this is X, 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 but it's a variable value. So the first thing I would do is refine this position. So I double click here and I say, let me refine the position on this. And click away, and now I'm refining the position. That's 1 added parameter. Let's see how that does. Not much. So we're pretty close to where we should be on this. What else can I refine? Well, notice I have line broadening. These are isotropic temperature factors, And there's some value from the CIF file, but maybe these aren't the value that I want. So let me refine those. And generally, I will refine the heaviest element first, just to, and U is the isotropic temperature parameter. Let me just refine this first and see what I can get out of this. And you can see it improves quite a bit. We reached 39, so we dropped a little bit, and now the value of this is 0.02, so it's much larger. So somehow these are probably too small for our particular data set. Let me now do the magnesium, and let me do X and U for the oxygen. Let's see if this works. Sometimes if you allow too many parameters to refine at once, you can get, it can run away on you. You have to be a little careful, but I think this is going to be okay. Okay. So we're getting better. We still aren't there yet, but we're getting a little bit better. Okay. So we are now refining everything that we could refine except for the fractional occupancy. I'm not going to touch that right now, but you'll notice that I can choose F as well. And that means the fractional occupancy can change as well. But I'm not going to worry about that for the moment. So I'm finding everything I can refine here. Notice that these are all 0.02 or 0.03, but they look very stable. They look like they're going to stay there. I'm going to refine one more time and sort of get a baseline for this particular arrangement of things. Okay. So let's see what else we have. Our background, instrument parameters, we don't really refine these at all. Sample parameters, I could adjust the sample parameters. And what I would like to try to do is let's try this one and see whether that improves things. And it doesn't look like it does much. So cancel that out, unrefine. Let's look at the Y. From what I've been told from the beamline scientist, only one of these two is really ever used. And it turns out that in this case, we don't need to use either one. So our instrument parameters are good. The position of the peaks is good, but our intensities are way off still. So what are we left with? Well, we're left with these parameters here. The strain broadening and potentially preferred orientation, which I wouldn't think is much of a problem, but we may have to use it. So let's first look at size broadening. So I'm going to refine this and see what I get. And so this is making a significant improvement. So now we're doing much better. You notice that the error, which is here, is small. If I go up here, you can see and plot this, you can see a little bit more information. You can see the peak positions have the tick marks, and the light blue is the difference. So if I look here, and I zoom in right around here, you can see that the difference is much better now, although it's still, there is significant difference. There also is a peak here, which I'm not fitting, so there must be some small impurity. So can I do any better than this? Well, let's see. Let's go back to the data. And this is telling me that the size broadening is for 10 micron sample size. And this is isotropic. So you're assuming you have sort of a spherical particle of 10 microns. Pretty big particle, but remember our energy is very low, is very high. And so a big particle, you know, the absorption length is quite low. And so you can tell the difference between big particles and of this size. Let's take a look at microstrain and see if that makes any difference. So we were about 25. And you'll notice that what happens often is it gets bigger and then it gets smaller again. So it's popping out of the current minimum and then going back to a better minimum. And now we're starting to get a little bit better. Okay, so I can look at this in a log square root plot, which can be helpful, or a log plot by typing L or S. So that's square root. And I think log, oh, well, let's see, log is N. So if I type N, it'll go to log plot. So you can see we're not doing as well as we thought with the background. And it could be that much of the error that I have is because of the background. And you can see it in a log plot. You can see it in a square root plot a little bit, but you notice that this is pretty flat, and 6 parameters for the background gets you a pretty flat background. So it looks like I need to use more than that. So let me go to 9 and maybe even 12. And so let's refine again and see how we do with this. Don't crash on me, please. This is taking longer than expected. There we go. I may have to roll back and start again with some of these parameters because often you have an issue. Yeah, you see, so this is added these additional parameters and it sort of rolled over and died. Let's see if I can do a little bit better just by doing one of the parameters. See if that helps. Okay, this doesn't look good. So what do I need to do? I need to roll back the number of parameters that I'm actually fitting, and then start again with the background. See if I can improve it. It doesn't look like it's going to work here. So this is a little lesson. I should have looked at the background beforehand to make sure that 6 parameters was sufficient. And this is not great. So what happens possibly is you get into one of these places where you're in a local minimum and then you go off somewhere else, and that's not good. So let's go back to the sample parameters and cut down, magnesium, and unclick these and let them go. So we're pretty close. Atoms, let's uncheck these. If I do this, I can uncheck all of them simultaneously. So also, if you're in this, you can see where the 3 atoms are relative to each other, which is also useful. And you can do a little bit more than that. You can draw multiple unit cells and make the whole thing bigger, show all the multiplicities and everything. You can do a lot more graphics than this. All right. So if I now have only the histogram intensity, which is here in sample parameters, I only have this and the background. And let's see if I can do a little bit better. See if this will work. I don't know. It doesn't look good. So the other thing you can do is basically start fresh. Sometimes it's useful to start fresh. And the third thing I can do is cut the data. So I only look at data where it's relatively flat, because this is certainly not working very well. I'm having some trouble adding those additional parameters. Yeah, this is not going to work well. Now, one good thing about GSAS is it keeps all the backup files, so you can roll back to a known working model and start over again. So I'm going to not load the new result. I will go back to the background and take it back to 6. And so leave it like that. But now what I'm going to do is I'm going to change my limits. So instead of starting at 0.5, I'm going to start at 2 theta is 5. Because there's no peaks there, so I'm going to start with that. And now I'm going to refine this. Hopefully this will work a little bit better. Now there's something wrong here. There could be, I just loaded the newest version of the code, so there might be something funky with the code. I'm going to stop this for a moment and save the project and then close the program and then open the program again. You see all these backup files. You can pick any one of them and start again. If you can figure out what they each are. Okay, so I've cut the data here. Let me see if this behaves a little bit better now that I have. It doesn't look good. Yeah, there's something funky going on here. I wonder what it is. I'm not happy. This does not make me happy. Yeah, this is not great. Okay, let me, it's easy enough to start fresh. There's something that's not quite working here. So I'm going to cancel this. Let me start with a new project. Not save this. And I'm going to just import the data really quickly. Again. Okay, and then I'm going to import a phase. That's fine. Associated there. And this is not uncommon that you have to go back. If you're not satisfied, you start fresh. It doesn't take you long and it's worth doing because sometimes you get into the wrong local minimum and you'll never get out again. So let me start by setting the background. Instead of 6, I'm going to go with 9 to start with. Usually I have no problem increasing the background limits. I don't know why this is. I'm going to change the limits. In this case, I'm going to go from 4 to 50. And then I'll go to, yeah, that's good. And then I'll go to the sample parameters, make sure my histogram is set. And let's see what we get here. And let's call this ALT. That way it's different. Let's see how we do. So you'll notice now that it's not fitting anything out here. Right? So we've reduced this. We've cut it off over here. Now let's take a look at the log plot again and see how we're doing. Okay, so we're doing okay here. We're not doing okay out here because we're not fitting these peaks yet, which is fine. But we'll get there. Okay, so just to move quickly through, my sample parameters are 1.01. My lattice parameter needs to be refined. My atoms, it's easier if I start very close to what we had, 0.02. 0.02. This way I get a little head start. And here I'm going to leave these off for the moment. So I've just added the lattice parameter now. And I do a refinement and see how we do. Okay. All right. So now I'm going to just keep going with this and see how well I can get this with the size. Actually, the strain was the one that did the most work. So let's just refine with the strain first. Sometimes you only need either strain or size, but not necessarily both. Let's take a look at the square root again. See how we're doing. That's not bad. Let's look at the log. That's better. I'm not totally happy with this yet. Let's see if if I can increase by 1 the background in this case and see if this improves things. Yeah, this is more stable. For some reason I was in a funny mode. So this one more background parameter doesn't make much difference. Let's go to 12. And that's usually as much as I ever go. And it may be too much. We'll see. Yeah, as you can see, we're getting small improvements, but not much. So we're pretty much there. Okay. So now we have, the only thing we have left to do is to allow the atoms to move around a little bit, especially the oxygen atoms, and to change the size. So if I do a refinement on the size, let's see how we get. We were at 13.1, and the size may or may not improve things. It doesn't seem to improve things very much. So I'm going to reset the size and clear it for the moment. So the microstrain seems to be the one thing that helps most. For the atoms, remember we had all of them are U, and then this one is XU. And this should be about as well as we can get without preferential orientation, which I don't think is important, but we can try it. So it's about 11. This is not bad. This is certainly better than we had before. And you can see that the differential parts are not too big. We're missing a little bit. There's a lot of sharpness to these lines, so that's a line profile problem. But more importantly, you can see an extra peak here, an extra peak here, an extra peak here, and as we move downstream, there's another extra peak here, which we're not fitting. And there's another one here and another one here. So in this particular case, there's another phase in there. And we don't really know what it is. And we're clearly not fitting it. So 11 is probably as good as we're ever going to get a refinement with this particular phase, sample because of the peaks that are excessive. Oops. So these extra peaks are going to limit the refinement. Now there's one here too. So if we were trying to figure this out, we would identify these peaks, do a little bit of peak search, and try to find what phase it might be. If it were a good phase to that we think is important, then we go back and refine it. And you don't see these peaks too well if you don't look at the log, or if you don't look at the square root. Because if I look at the actual intensity, these peaks are really tiny. The only one I really see is this one here. And the others are very tiny and not very visible. So this is not a bad refinement. If you look here, it says it's 11.768 for the residual. But the phase residual for that phase is much better. It's 4.3 or 6.5, which is really quite acceptable. All right, let me save this and let me close the project. Do a new project. Okay, so that's a data set for BM, 11 BM. I also have some data for the Brooker the X2 phaser. And I think it'd be useful for you to look at that too, because that's the kind of data you'll probably be more often looking at. So let's open some of that data. Import powder data, GSAS powder file. Let me see what I got. Oops, physics 570, 21F. Let's go to gallium 203. So this is data that we just have picked up recently. This is gallium 203. This is the one I want. Now you notice it's asking me for an instrument parameter file. That's what it does with the GSAS data because it doesn't contain that instrument parameter file. I know my instrument parameter file is up here. It's called IIT D262 instaparam, which is the parameter file that seems to fit the best. Okay, so here's my data. You'll notice something that compared to the powder data from 11 BM, this has a lot more noise to it. The counts are lower. The peak widths are bigger. That could be the sample itself. And there's a background that's much more sloped at low angles. And that's because of the finite slit size and the takeoff angle of the tube that you measure. So this is a phase of gallium 203. The question is, what phase of gallium 203 is this? And so let's start a new session. It'll probably complain. Okay, good. And I'm going to look for gallium 203. And I can do a search. I think this search here is the gallium 203 search. So let me run this search. And we're going to get about 18 or 19 solutions. Now, there are various structures for gallium 203, and you can see it right here. They're not all the same, right? This is a C-centered monoclinic lattice with a beta of 103. This is a rhombohedral structure with a 120-degree angle, and it has an A parameter of 4.98 and a C parameter of 13.433. And this is a primitive orthorhombic cell. Now, if you look more carefully here, this says the real structure of epsilon gamma 203 and its relation to the kappa phase. So this already is a big red warning sign to me because it says there's a lot of gallium 203 phases if we've gotten to the epsilon and kappa phase. Usually they start with alpha and beta. And so there's a lot of phases for gallium-203. We better find the right parameter file. This one says it's the alpha gallium-203 structure. So let's choose that one. Then this one says the crystal structure of beta gallium-203. So let's choose this one too. And so you can see the monoclinic looks like it's beta. The rhombohedral looks like it's alpha. This one is a spinel. It looks very much like the one we just saw. This is structures of uncharacterized polymorphs of gallium-203. So I don't know what the heck this is, but it's certainly something. I'm going to select this one too. And then we're going to take a look at them a little bit. This is another one. It's yet a different one. This is a hexagonal structure again. So let's take a look at that one. Let us look at comparing the powder diffraction patterns and see what we can get out of this. So the question is, which one best resembles our current data set? And then we'll choose that and we'll work from that. So looking at this and remembering that there can be preferred orientation, it looks like this is the guy. If you just look at this structure, you can see it has all the right peaks here. It has this clump of peaks with a medium, big, small, big, and then two peaks together, and that's exactly what we have here. So my guess, since this is probably the beta, is that we have beta gallium-203. So that's what we're going to select to download. So let me uncheck these and pick out the beta, which is this one. And I'm going to download the CIF file. Okay, so I'm done with this. And now I will bring the CIF file into my into this directory. And it's called entry with collection code 34243. And just in order for me to tell what it is, I'm going to call it gallium-203 or beta, gallium-203 beta underscore and then collection code 34243. So this tells me now that this is the beta phase. So I have my data. I'm now going to import the phase. And if I go up to here, there's my beta phase. And this is it. I'm just going to call it that. I'm going to associate with this powder. And there we go. All right. So we do the same thing. Now I'm going to use probably 9 parameters for the background here. But I think I'm going to cut the background at 14. So the first thing I'm going to do is set this limit to 14. And then I'm going to change the background to 9. And then sample parameters. Typically with this kind of intensity, I'm going to set this to 100. I'm going to turn it off. So I'm going to set a fixed amplitude. I want to get the lattice parameters right. So I'm just going to set a fixed amplitude and see what happens. This is a very important thing to do for this kind of data. If you're not sure whether you have sample displacement or anything that would shift the peaks around, you're better off not setting the histograph factor, scale factor to vary, or else it might go to 0 really quickly. So and everything goes messed up with everything moving. So you want to allow only a few parameters to change at a time. So right now I'm just going to do the background And I'm going to set the scale parameter, see if I get something. I have no idea whether this is going to work. Okay. Okay. So this is very poor fit, obviously. And the reason is the peaks are not in the right position. You can really tell here. If you zoom in, oops. You zoom in, you can see the peaks are just not right. And the intensity is too high. But keeping the intensity constant allowed me to sort of, it's going to allow me to get close to the peak. So the first thing I'll do is I'll cut the intensity down by a factor of 2 and leave it constant. And then I will allow the lattice parameter to vary, because that's usually the first thing I want to try. So we can see what happens as it tries to refine. The lattice parameter is moving slowly towards its better position, and it's getting better, but I need to do this several times. So I'm at 81, it's dropping to 75, I'm getting closer. But there will be a limit at which point I will not be able to do any better. It's better, but I think I'm probably reaching the limit. And at this point, I could probably set this up to refine 10 times instead of just 3, because I know I'm not going to be too far off. So let me change the controls to refine 10 cycles. Okay, so what haven't I allowed to change? I haven't allowed the histogram scale factor. So now the last parameter is getting close. I can turn this on, but I prefer to turn on the sample displacement first, because I know that this is a problem in our diffractometer. It's always a potential problem. So I'm going to calculate this and see if the lattice parameters and the sample displacement both get me very close to my peaks being in the right place. And it's doing much better. You can see we're getting very close now. It's continuing to get better. And now I can allow my histogram scale factor to change. And this should lock in right away. So we're getting about 16.2, which is not great. We should be able to do better than that on this machine. Now, clearly, there's some additional peaks here. There's some impurities that we're not taking into account. So let's take a look at the square root. The background is pretty good. I'm pretty satisfied with the background. I could add another couple parameters here, but let me do that later. And clearly we're not fitting these 2 peaks. And so we're going to have a problem with that. However, if we zoom in, we can see that one of the bigger problems is the peaks are too narrow. You can see how narrow this one is compared to the actual data. And so we have to fix the narrowness of the peaks. And we also have a sample displacement. So the narrowness of the peaks is due, as we had before, to particle size or microstrain or preferred orientation also can contribute to that. So let's try with the particle size. And remember, this is hexagonal. This is rhombohedral. So the lattice parameters, there's an A and there's a B and C. Oh, this is orthorhombic rather, sorry, orthorhombic. So we could have preferred orientation. We could have uniaxial stress. And I don't know whether that's the case. We'll just have to see. Right now, I'm going to say, instead of uniaxial, I'm going to say isotropic. And so let's see how that does. And this data I actually haven't refined before, so I have no idea how well it should work. And I may have to try it several times before I get what I like, what I think is a good solution. So that's improving things a little bit. You notice it goes up and then comes back down and finds a new minimum. And we're getting down to 10. Our refined phase is on the order of 3.08052, which is not bad. So at this point, I'm pretty happy with the lattice parameters are pretty good, I'd say. This is monoclinic. I'm sorry, it's monoclinic. I'm not going to try isotropic preferred orientation, although I could try it and fool around with it. The particle size is not that small. This is microns, so this is 120 nanometers. I have not tried microstring. I could do that, but I think I'd rather go look at the atoms. So in this structure, you notice that all these parameters can be variable. And so the first thing I'm going to do is allow the x coordinate of these to vary. And then since I know my instrument, this is probably way too small. So I'm going to cut this back by 1 decimal place. This is probably fine. This is fine. This is fine. Actually, this could be a little bit bigger, but I'm just going to leave it like this. And now I'm going to refine again. And let's see how we get. Remember, we were down about 10. We'll see if this improves significantly. Not a lot. It doesn't actually improve much at all. I don't think it even improved. It just went a little bit higher. And so the atoms moved around a little bit, but not a lot. Let me change the U. Let me change the X on the oxygen. See if that helps. And again, this is a real-time demo. I haven't done this before, so I don't really know how well we'll get. That doesn't seem to do a lot. You can look at the parameters. They're not changing a whole heck of a lot. Yeah, it's just a little in the 3rd decimal place, maybe. Let's try the U. Aha, that certainly improves things significantly. So now we're getting to a point where this is not good. That's negative. That shouldn't be negative. So these aren't great. I'm going to set this back to 0.101. And this is going to set to 0.01. I'm just going to set them all to 0.01. And knowing that I can probably refine those for the gallium, but for the oxygen, they're really not going to be very stable. So I'm going to turn the oxygen off. And that's because for X-rays, oxygen's light, so you don't have a lot of density. So let's see what we get. So we got to 9.6. Okay. All right. Stable refinement. These values are reasonable. Okay. All right. So what else can I do? I can try microstrain. But let me try, before that, let me try preferred orientation, because preferred orientation is certainly possible with this structure. Well, that's too many parameters. Let me set 2, and let's refine that and see how we do. It might be that we're at the limit of the structure because of the impurity phases. I just don't know. So this didn't change much. And you can look at the texture value, 1.002. This means that the sample's really very random. These are very small. So I wouldn't consider this having any preferred orientation. Let's now try the microstrain. I'm going to turn this off because it didn't do us any good, and try the microstrain. See if that improves things a little bit, or if it just makes things worse. It does not change much. Again, both the microstrain and the small particle size. So this doesn't change much, but it looks stable. The only other thing I could try is if I had a preferred orientation for the uniaxial stress. So, or using ellipsoidal if size. I don't think that's a problem with this. I think they're probably more or less spherical, but if you do this uniaxial, you have to choose a value, right? You have to choose a unique axis. And that's not really clear what would be a unique axis for this orthorhombic structure. For a tetragonal structure, you might choose the 001 direction because that's the basal plane. For a hexagonal structure, you might choose the 001. For this case, I just don't know. Let's see if that improves anything. And I can always roll it back. I'm getting pretty close to the limit of what I can do here. It doesn't look good. Yeah, it goes way off. This is not good. It is definitely not happy. Yeah, we're gonna stop it right here. Hopefully I can get it to stop. Yeah. So I'm going to turn this off, turn this back to isotropic, which is appropriate. And that's pretty much where I am. So at this point, this is the best I'm going to get. Maybe I could improve the background a little bit. Maybe if I found the secondary phase, I would be able to do something about that. It might be that there's another gallium dioxide or sesquioxide phase, and you can go and really spend some time on this if you really want to know. But there's a bunch of these little peaks here that I should be able to get. There's more peaks over here, and I should be able to figure this out. It's a minor phase. I don't need to worry about it too much right now. The peak shapes look good. The residual is relatively small. So I would say that this is pretty successful refinement. And it's probably good enough for what we need to do for this particular project that we're doing. I'm going to be more interested because if you get away from the square root, you'll see that it doesn't look as bad as all that, right? It looks pretty good. We still aren't doing well here with this peak. That's the worst. The big peaks tend to sometimes be a little bit off. And we'd have to look at other possibilities like extinction. We've decided preferred orientation doesn't work too well. We could try a different kind of strain broadening. But for the moment, I think this is good enough. And what I would do after this, as you may have noticed, I had a different file too. I had a file where we substituted 30%, or pardon me, 15% of the gallium-2, the two galliums, by iron. And, and we wanted to know if we get the same structure, because iron forms a hematite structure, Fe2O3, so it will probably only dope into the gallium a little bit. So I think hopefully that's, I have showed you enough. For today, I'm going to stop recording. You guys